Let's take a look at some examples of application questions that are going to require us to work with the derivative. Before we do this, let's quickly refresh what we looked at in the end of the last video, and those are the steps we're going to use to approach problems like this. So we're going to draw a diagram if appropriate, create the relevant equation, ensure the equation is defined in terms of only one variable, consider the question, do we actually need calculus to solve it, look for telltale calculus words that indicate that we need to find the derivative. If there's any maximums or minimums involved, know that we need to set the derivative to our function equal, or our derivative function equal to 0 at those points. And make sure we've answered the original question. Let's take a look. Consider the circle. Ooh, we haven't worked with circles yet. X squared plus y squared equals 3. Find the dimensions of the largest rectangle that can be inscribed in the circle. And so initially we might be thinking like, oh, I'm not really sure how to start. I don't know about working with circles. I don't remember doing that. Or maybe I do remember a few things. We just want to start by doing something. So let's write that down. Do something. I at least know what a circle and a rectangle look like. So maybe I can go ahead and start drawing that. Maybe I remember a few things about working with the equation of a circle. For instance, the center of this circle is going to be located at 0, 0. We have worked with circles before, just not in this course. And basically, it's like x minus x1 squared plus y minus y1 squared equals r squared. So these indicate how offset the center of the circle is from the origin. We don't have any additional values in here with the x and the y, so it's going to be centered at the origin. That's how we knew it's at 0, 0. It equals our radius squared, and our radius here is our radius squared here is 3, so that tells us the radius of our circle is equal to root 3. And if, let's say, you did not remember this stuff, then this would be the type of thing that we could maybe look up. You're thinking, I don't remember the format of the equation of a circle. I'm not sure what that means. Then that's something you could refer to in your textbook or online and then proceed from there. Obviously, if this was on a test or something, that'd be a little challenging, but I would hope that I wouldn't assign you a question like that when you hadn't had some refreshing knowledge on that or hadn't learned it in the course. A couple other things to keep in mind. We're trying to make the largest rectangle. What does largest mean in terms of a rectangle? Well, it means we want the largest area. Area is another keyword I can maybe do something with. We also know that word largest, we just saw in our previous question, that when we're dealing with maximums and minimums, that means the derivative of our function, at that point is going to be 0. And what else? We're working with area of a rectangle. So I know a formula involving the area of a rectangle, which is area equals length times width. So we have a relevant equation. We see the word inscribed inside, or inscribed in, and that indicates that we're going to be inside the circle. And any other keywords to consider? I think that's it. We know what a circle looks like, and we've described how we can graph it and what it's going to look like. Found some other keywords. We're looking for find the dimensions. So we need to know the length and width. Largest means maximum. So maybe we're going to need the fact that the derivative at a maximum is equal to 0. We want the largest as in largest area. So we have keywords area of a rectangle, and that's going to give us that formula. And now this is defined in terms of two variables, but we already saw in our previous video how we can convert the area of a rectangle to be defined in terms of just one variable. And we know the other keyword inscribed is going to mean inside. And once again, if there's ever a question or a vocabulary word or a word in a question that you aren't sure of, then you should pause and look that up and make sure you understand. Because sometimes you might understand the whole question and there's one word that, well, I wasn't sure what it meant, so I just guessed. If you guessed wrong, that may have a big impact on your answer. All right, let's go ahead and draw our diagram. You'll notice when we looked at the previous slide that drawing a diagram was often a box on its own. It's not even step one. I often do the same thing when I describe problem-solving processes in my other math classes or science classes, and I kind of say drawing a diagram is step zero. You're not even solving yet. It's just the first thing you do to help visualize. Also, sometimes we don't need it. Sometimes it's quite obvious, so it can also be step zero because sometimes we can skip it and go straight to step one. All right, let's go ahead and draw this. So we have a diagram to start. All right, I'm still getting used to using the shape tools in this program, so I've gone ahead and sketched this while the video is paused, just to get it nice and neat. And now let's add some labels. So I'm going to have my x-axis and my y-axis. We know our circle has a radius of root 3, so we're going to be at root 3 here, and at root 3 here, negative root 3 here, and negative root 3 here. What else do we know? Well, I know the equation of my circle, x squared plus y squared equals 3. Could also define this, rewrite this as y squared equals 3 minus x squared, or y is equal to plus or minus the square root of 3 minus x squared. So we kind of have I can't use the word function because, you might remember from advanced functions, this fails the vertical line test. A vertical line intersects our function at more than one point, but it is an equation. So we do have an equation for our line, which we have kind of defined and simplified here a bit. We also know that we want to inscribe a rectangle on the inside. It's going to be a square because we're drawing it inside a circle. We know about circles are symmetrical all the way around, so our rectangle has to be symmetrical as well. So I'm going to pause and sketch my square in here for a moment, or my rectangle, and then we'll continue with our labels. All right, I think that looks pretty reasonable. Let's go ahead and add some more labels. I know this is going to be at right angles because it's a rectangle, so we can add that label. And we're going to have our length and our width. I'm actually going to put the labels on the inside just to keep this clean. This will be my length. This will be my width. And what else do we know? Well, we can also define our points here as x, y, negative x, y, x, negative y, and negative x, negative y. So we haven't actually done any calculations yet. We haven't added any done any calculus. We're just trying to express things as cleanly as we can based on what we know. We can also define our width as being 2x values. So if our x value is how far from the y-axis I've traveled, I know those distances, so this is going to be x, and this is going to be y and y. All right, let's see what we can do now that we have a labeled diagram and a few equations. First of all, we need a relevant equation. We do have one. We have an equation here for the area of a rectangle, but we need to define it in terms of a single variable. So I'm going to need two equations, and then I'm going to substitute one in, and we'll end up defining everything in terms of one variable. So let's describe what we're going to do here. Actually, let's keep a track of our steps off to the side somewhere. So step 1. Actually, I am going to call it step 0. Step 0 was to make our diagram. And we also added as many labels as we could that we thought might be relevant. Next step, we're going to work with our equation. We're going to find, from what we know or what's given in the question, a relevant equation, and then define in terms of one variable. So let's work on that. All right, step 1. We have area equals length times width, but I'm going to need another equation that uses length and width so I can rearrange and set it equal to length or width. Well, I kind of know that the area is also equal to 2 times x times 2 times y. I can rewrite this as 4 times xy. And what do I know about either of these variables? Do I know any other equations for x or y? Yeah, I got this equation right here. I know that I can define y in terms of x based on the equation of our circle. So let's go ahead and do that. And we'll label off to the side what we're about to do here. We're going to use y equals root 3 minus x squared to express a in terms of, in terms of a single variable. And you might be thinking, Mr. Strike, over here we had plus or minus. Why are you just using the plus here? Basically, I'm just going to deal with the top half of my equation right now, because this part is a function and this part is also a function, so it doesn't really matter which one, but I can't work with both at the same time because then it's not a function anymore. So I want to work with the function, so I'm just going to work with half. That's going to be good enough. I can define my points from there, and then by symmetry, if I know these values, I'll be able to flip them and apply them down there. So I basically am only doing the calculation for one set of values, and then I'll reflect them over to deal with the other values, the other points I need to know on my graph. On my, graph is the right word, on my diagram. All right, let's keep going with this question. So we're going to have a is equal to 4x, and we're subbing in a different expression for y, root 3 minus x squared. We can rewrite this once again. A equals 4x, 3 minus x squared to the power of half. So we have successfully found our equation in terms of a single variable. Am I going to need any calculus? Do I have enough information here? Well, do I know what the area is? No. Do I know my x value? No. So I have two variables that I can't just solve it the way it is. I'm going to need more information. Do I have any numbers in the question I haven't used yet? Well, I've already used these, and that involved using these. And I've already rearranged them here, and I've defined things here in terms of like the radius, and I know I'm looking for like the x and the y, and this is 2 x's and this is 2 y's, but I have no new numbers. I have no new pieces of information that I haven't used yet, except for there is one number we haven't used, and that's our 0 here. I haven't considered the fact that I need to find the maximum area. And basically what that means is, in order to find the maximum, I need to find a point where the derivative is equal to 0, which means that's kind of one of our telltale words here. If I'm going to find the maximum, if I'm going to optimize, I'm going to need the derivative. So we're going to need to define the derivative of our area equation here. So step 2, we're going to find the derivative, because that's what our keywords, that's what our instructions suggested that we needed to do. So step 2, we're going to be finding the derivative. And let's think about what tools we're going to use here. Well, I have this expression and this expression, and they're being multiplied together. So I'm going to use product rule. And as I've done before, I'm going to write that out to help me keep track and so I don't forget, and also to show you. I don't teach calculus like every semester, so I really do find it helpful when I'm working through this stuff on my own. I really do write this stuff off to the side to keep track of my work and to kind of do my pre-calculation. So since you are also, well, I have learned this before, but you are learning this for the first time, so you need maybe some extra support along the way, I do encourage you to write things like this in the margin of your notes or on a scrap piece of paper to help you keep track as you work through things. So we remember that f prime of x is going to be g prime x times h of x plus g of x times h prime of x. We also notice that our second function here is a function inside another function. There's some operation being applied to everything inside the brackets. So I'm going to have chain rule as well. Remember, that's for composite functions where f of x is equal to g of h of x, and we'll find our derivative. So, or we'll find our pieces. Actually, derivative first. F prime x equals g prime h of x times h prime of x, or we could also write g prime of u times u prime. Let's find all those pieces. My g of u is equal to u to the power of half. My derivative is going to be half u to the negative half, or 1 over 2 root u. My u, which is my h of x, is the inner part, so that's equal to negative x squared plus 3. Or you can leave it as 3 minus x squared. I just like to have my polynomials arranged in descending order of exponent, like the kind of proper notation. And u prime, or h prime x, is equal to negative 2x. So I've already done this work off to the side. That's going to come in handy as I work through this problem. So let's go ahead and do this. So I'm going to have a prime. Actually, we'll keep the same color to be consistent here. A prime is equal to, so I'm using my product rule here, g prime, so derivative of 4x is just going to be 4, times my second factor, which is 3 minus x squared to the power of half, plus g of x, so my first factor remains unchanged, and then the derivative, we're going to use these pieces here as we do our chain rule. So I'm going to have g prime of u, so I'm going to have half u to the power of negative half, and u is my negative x squared plus 3. So remember, what's inside the brackets stays the same, and actually to be consistent, I'll leave that as 3 minus x squared since I left it that way here. And even though this looks a little different than this, they're still the exact same thing. So I'm not done with the chain rule. I've done my g prime. I have my h of x, or my u, inside. I still need to do my h prime x, which I found here is times, so times negative 2x. All right, all my pieces are here. It's just a little messy. Let's go through and tidy this up. So we're going to have a prime is equal to 4 times 3 minus x squared to the half, plus, and I can multiply these terms together. 4 times negative 2 is going to be negative 8. So I'm actually going to kind of take a step back here and write negative 8 x times half, so over 2 times 3 minus x squared to the negative half. Tidy this up a little more. A prime 4 3 minus x squared to the power of half minus 4x 3 minus x squared to the negative half. All right, are there any greatest common factors I can take out? Yes, I have a 4 in front of each term here as my coefficients, so let's take that out. A prime is equal to 4 3 minus x squared to the power of half. Negative 4 divided by 4 is negative 1, so minus x times 3 minus x squared to the negative half. And these are the same, right? So I can just factor those out. A prime 4 3 minus x squared. Oh, wait, I can't do that. Why not? Make sure you're paying attention to the sign of the exponent. This is a plus. This is a negative. We can't do that. I can rewrite this in terms of positive exponents, though. So I can't factor it out, but I can do something with it. A prime is equal to 4 times 3 minus x squared to the power of half, or you can make it a square root if you wanted. Sorry, I just realized I made a mistake. When I did this part, 4x times negative 2x, it should be negative 8x squared. So I'm going to go back and add that in. Sorry about that. It doesn't really change anything. We haven't gone too far, but I am going to put that back in because it's kind of important. And I'm going to take a quick step back here because we can still pull this out as a greatest common factor. We just can't pull it out directly. We just need to be careful dealing with the fact that our exponents are different. So don't just yank it out. Consider the fact that the exponents are different and how we're going to deal with that. We know with greatest common factor, we're pulling out the factor that's smaller. And being to the negative half means it's going to be smaller because it's 1 over that value instead of just that value. And so this is the one we're going to pull out as a greatest common factor. So we already pulled the 4 out. Now let's pull out our more complicated term. So a prime is equal to 4. We're taking out the smaller one, so we're going to have 3 minus x squared to the power of negative half. What's going to be left inside our brackets? Basically, we have something to the power of half being divided by something with the same base to the power of negative half. What do we do when we subtract? What is our exponent rule, or what is our quotient rule for dealing with exponents? Well, we're going to subtract our exponents and leave the base the same. So it's going to equal b to the half minus negative half, so plus half, or b to the 1. And in this case, our b is equal to 3 minus x squared. So I'm going to erase this to have my space back. Well, let's go ahead and write that in. So we're going to have 3 minus x squared to the power of 1. I don't need to write to the power of 1. It's implied. Minus, and this was my common factor. I just divided out, so it's going to be canceled. And so I'm going to be left with x squared. This is looking tidier by the moment. Finally, let's collect some like terms, and let's use up our negative exponent and move those terms to the bottom. I'm going to be left with 4 times 3 minus x squared is minus 2x squared over my term on the bottom, 3 minus x squared to the power of half, or square root. So we have successfully found the derivative of our function. So where were we? Where were our steps? Step 0, diagram and labels. Step 1, equation. Step 2, find the derivative. And because we are dealing with the maximum, we are going to set our derivative equal to 0. Set derivative to 0. So let's go ahead and do that now. In step 3, we are setting our a prime. I shouldn't write 2 equals signs, so I'll just write 0. Well, let's do it this way. A prime equals 0. So I'm going to have 4 times 3 minus 2x squared over 3 minus x squared to the power of half equal to 0. When is this term going to go to 0? It's going to go to 0 when our numerator equals 0. So, and we don't even need our whole numerator. We just need this part right here, because 4 is never going to equal 0. But I can set a value of x such that my factor there equals 0. So we're going to set 3 minus 2x squared equal to 0. And let's solve for x. Let's find the value that satisfies this equation. We're going to have 3 equals 2x squared. 3 over 2 equals x squared. X equals plus or minus the square root of 3 over 2. And here's another question. How do I know that I just found a maximum point and not a minimum point? Well, the equation we are working with here is finding area, and area has to be positive everywhere. So actually that doesn't help. It has to do with the shape, not whether the values are positive or negative. Well, we do know we're finding area. We can stop and visualize for a moment. Area as a function of x, and x is related to our width. I know if my rectangle has a width of 0, the area is going to be 0. I know if it has an infinitely long, like basically if the width is like this, 0, then the area is going to be 0. On the other end, if the width is really long, my length goes to 0. My area is also 0. And everywhere in between, I have positive areas. So my area is going to increase to a certain point, top out, and then decrease. So I know that this point I just found, where my derivative was equal to 0, has to be a maximum. And there's other ways to prove that using second derivatives, but we haven't learned that yet. So instead, we can just do our quick little visualization here. And I am going to erase this because I need the room. But if you want to copy that down, you can pause the video and do so now. All right, so we found the x values that satisfy this equation. So what? What did the question actually ask us to do? Have we actually answered it yet? If we scroll back up and take a look, the question asks us to find, the question asks us to find the dimensions, the length and the width. I don't know the length and the width yet. I found my value for x. I know that I can only use the positive values, so my negative values are inadmissible because I can't have a negative length of a rectangle. I can have a positive length though, and I know that my two x's added together represent my width. So let's actually finish this off. So let's find our required values. And then we'll 5 confirm that we have answered the question. All right, so step 4. I know that the width is equal to 2 times x. I know the value of x. I just found it here, and I know only the positive value is admissible. So 2 times root 3 over 2. And that is our exact value. We cannot simplify that any further. I could express it approximately, which would be approximately 2.5, but I'm going to give the exact value. We also need to find the length. Do I know a relationship between the length and the width with a number? Let's take a look. Which equation do we have that we can use? I think we should go ahead and use this equation. I know y defined in terms of x, and I know my x value. So let's solve for y and then use y to find the length. So the length is equal to 2y. The length is equal to 2 times, and y is equal to, we're just going to worry about the positive component because we want a positive length. Positive root 3 minus x squared. Let's plug in our values. L equals 2 root 3 minus x is root 3 over 2 squared. Length is 2 root 3, and a square root squared is just going to be itself, so minus 3 over 2. So length is 2 root 6 over 2 minus 3 over 2, which is going to be 3 over 2 once again. So length equals 2 root 3 over 2. Or this just confirms that it's a square, and actually, if we had remembered what I said earlier, which I forgot, that this has to be a square because it's inside a circle, it's symmetrical, the length and the width have to be equal. So we've proven that mathematically, but technically if I just use logic, I could have proven it that way as well. So let's finally answer our question. Did we have any units of measurement? I don't think so. No centimeters or anything to worry about. So let's just state our conclusion. So step 5, answer the question. Therefore, this rectangle, well, we'll mention, is a square and has a length and a width of 2 root 3 over 2 units. So when we don't know what the units are, we just use the word units. All right, so this was a bit of a question. I will not ask you a question like this on a test. I don't expect you to memorize how to do this specific question. The point here was to practice our problem-solving skills. How do I approach something that's challenging? Where do I start? And so those are the steps that we used as a guide. I've written a kind of a summarized version of what we actually did here to solve this question. Yeah, this is challenging. Don't feel like you have to memorize how to find the maximum area of a rectangle inscribed in a circle. Just try to remember this approach and how we deal with challenging questions. Ultimately, each part is relatively easy. So we know how to make a diagram. We know how to find an equation. This is a basic equation we've known for years. This is probably also a relatively basic equation we've known for years. We know how to find derivatives now. We know how to set derivatives equal to 0. I know how to solve a simple quadratic equation here. I know how to do some substitution to find my required values, and I know how to write the answer to a question. So we know how to do all these things, and this is true of many things we do, even in like advanced grade 12 math. The individual steps are not difficult. The problem is knowing how to put them all together. So that's why we look at this approach. We look at how can I arrange all this information that's being presented in front of me? How can I figure out where to start? What keywords do I look for? How do I know how to solve this problem? So once again, it's not a matter of, okay, I need to memorize the exact steps for how to find the area, maximum area of a rectangle inside a circle. Instead, we want to learn what are the skills I need to approach problems that I find challenging. How can I work one piece at a time and use the tools in my toolbox, either from this course, my calculus toolbox, my chain rule, and my product rule, or skills I've learned previously like making diagrams, knowing the equation of a circle, and so on. That is going to be the end of this video. I'd like you to try and work on the questions linked in Brightspace now as a chance to practice these skills on your own. Of course, if you need help, I do recommend asking your classmates, and sometimes students take that the wrong way and, oh, the teacher doesn't want to answer my questions. But one of the most important things we're trying to teach here, and like I just said on the previous slide, is we want to teach you how do I work on these problems on my own? How do I use the knowledge I already have? How do I answer things that are challenging? So one thing I'll often recommend, it's not that your teacher is unwilling to help in most cases, but we want you to be able to do it. So look at the resources that you have already. Do you have notes from today that describe some of the skills that you're going to need? Have you done practice problems earlier in class that demonstrate some of the skills that you need? Did you do homework questions in the last couple days that relate to this kind of question? Maybe it's the exact same kind of question. Maybe it was similar and it provided tools that will help you approach this new problem. Alternatively, it can be really valuable to have conversations with your classmates. So it doesn't just mean that, oh, I need to talk to the smart kid who knows the answer and they can tell me. Talking with people who are struggling, maybe they have a different piece of the puzzle and you can put those pieces together and answer the problem. Or maybe you're both missing information, but as you discuss, you can figure out, well, what piece of information are we using and are we missing? And do we have any skills or any knowledge from the day or any resources where we can look up and figure out what is that missing piece of information or how can I find it? And then if you're still stuck, then that can be a great time to ask your teacher and just say, Mr. Strike, we've had this conversation. We know we need this piece of information. We're just not sure of the method. And then your teacher can often point you in the right direction and say something like, oh yeah, we did this example question here. Take a look and try using this skill that's described here. Or here's the formula. You may have missed it in your notes. Here it is in your textbook. Or sometimes, and some of you have seen this in some of the homework questions, like, Mr. Strike, I tried this and I talked to people and we can't figure out how to do this. And then I realized, oh, okay, maybe I accidentally assigned a question where we haven't learned that skill yet. So there was a question a couple days ago that required chain rule because it was a composite function and we hadn't learned those yet. So then that's an opportunity for us to discuss and say, well, do you know anything about this? Do you have any ideas about how we might approach this? I might not answer this question today, but then that's a skill that we can look forward to learning. And then we can go back if we want, or at least have that skill in our toolbox for similar questions moving forward. I am going to end the video here. Please go ahead and try these questions. Do try them on your own for a little bit. Please use the resources provided and talk to each other if you need help. Otherwise, once you have done as much as you can on your own, I am, of course, happy to help.